What's up, folks? So today I'm going to code the training loop for Rectified Flow. I'm trying to make my videos shorter, so I'm going to break them into parts. Today I'm going to code the training loop, and then next time I'll build the backbone, the actual model. Well, I'll build the actual neural network model. So it's going to be based on UNet, but this time I'm going to... So this time I'm going to do the training loop, but the entire thing will be, right, Rectified Flow. We're going to be passing an image along a trajectory to a UNet model with a time step. And it's going to be similar to the UNet model I built before months ago, but this time we're going to inject the time step embedding. So we're going to be training on celeb A data. The reason for that is because, I want a reasonably small data set that we can work with that has a small number of features. So since it's all going to be faces, we're going to be able to see that the model is learning something that looks like a face pretty quickly. So we'll know that it's working. Because I don't want to spend too much time on this. I want to get to better and better versions of the model, right? So, and then because we have a small amount of data, we need to use convolutional neural networks, right? We need inductive bias in order to be able to learn something quickly. So eventually I'd like to use a diffusion transformer in latent space, right? But we need to build up some kind of baseline and build up our model from there so we know that things are working. So, okay, let's get started. So, right, I already have a lot of scaffolding code. So I have all these methods, stuff that I've done before, right? So, loading the config file, the main method, train test model. I have a data module, Python module that is going to load the data, the celeb A data, which is data that I've used before. So I'm not going to code any of that stuff over again because I need to make my video shorter. So anything that I've done before in any of my videos, I'm not going to do again. I'll just point you in the direction of the video, which admittedly I can do a better job of. So I need to start combing through my old videos and see where things are so I can paste the correct links in the description. So here's the celeb A data set, and here's the transform. Here's the transform I'm using. Just no augmentation, just simple cropping, resizing, and standard normalization. And right, so the train test model is going to initialize one weights and bias, load the data loaders here, and then we're going to code model optimizer, and then training loop. Training, validation loop, and then some inference. And it's going to use compute data and sample batch pixels. And then I had some other scaffolding, like just things that for plotting, plotting samples and loading things to weights and biases that I'm just not going to code. So, and then I have this UNet pixel space model that we're just going to leave like this for now, just the scaffolding. Matter of fact, I'll probably just put a neural network, a simple MLP in here, just so we can get something for our gradients to flow through to validate that our training loop is working. And then I'll code inference. I'll code up this sample batch pixels. This is inference. And then I'll stop the video. So hopefully we can get through this relatively quickly. I have a timer going just to make sure that I'm not going over roughly 30 minutes. So let's move through this. Okay, so model, UNet, pixel space, in channels, big, right? I have my config file just like usual, right? My local config file and my server config file. Most of the, if you've been following along with my videos, most of these variables you already know, right? So image size, batch size, normalization shape, time dimension. The time dimension is a new one. That's the dimension of the time step embedding. Num channels, num groups, num workers. Debug is a new one. It's just a flag to print stuff out. Weights and biases is disabled locally. I'm doing a small sample, so I'm sampling the original data set down so locally things can run faster. Inference peak number is basically on what epochs, like how, like every, it's the step number for the epochs that I'm actually going to do inference to validate that the model's working. Number of steps is the number of inference steps. So this is the number of integration steps. Right. Okay. So this brings me to the other thing I wanted to mention. So I did a theory video for Rectified Flow, and I wanted to mention that I switched things up, and I'm switching them back now, right? So in this theory video, I had x1 being the image, and I had x0 being the sample from standard normal. In this video, I'm going to have x1 being the sample from standard normal, and x0 being the image, because that's the canon way to do it. I had it mixed up. You can do it either way, it doesn't matter. But canon is the way I have it listed right here. X0 is the flattened image, and X1 is the sample from standard normal. And, right, so I'm going to code up this XT, right? We're going to have to come, right? So basically, we're just going to code this, this loss function, right? So it's the expectation, right? The subscript for the expectation is what we're sampling. We're sampling an X0, an X1, and a T, right? And then we're going to compute X sub T, and then we're going to compute this loss. We're going to pass values into our neural network right here, and then compute this ground truth, which is X1 minus X0, right? And then we're going to do inference, which is this equation down here. It's this iteration down here. So, all right. So, okay. Back to the training loop. All right. So so we have our model. Time dim equals config dot time dim p drop out equals standard 0.1 optimizer torch dot optim dot atom model dot parameters learning rate is config dot learning rate. Okay. Basic training loop. All right. We're going to have this is the dictionary that we're going to use to log things to weights and biases. And we're going to do for epoch in range 1 config dot epochs plus 1. We're going to do TQDM. We're going to do model dot train, right? First, we're going to do training, TQDM. Train data loader. So standard, you all who've been following along have seen me do this in every single video, but Rectified Flow is slightly different. So as with TQDM as train, I'll just call it P-bar. For images in P-bar, let's just say pass, and then we'll do validation, tqdm.write, epoch, flow. This is going to be eval. Oh. And with torch.nograd, Okay, standard training loop. Now, this is going to call our compute data function right here. And that's where the rectified flow computations are going to happen. Images, model, and it's going to return ground truth and a prediction. Okay. Okay. All right. Cool. So and then after validation, we have if epic mod config.inference peak num equals 0, or sorry, yeah, equals 0, then we're gonna do inference. Well, we're gonna call sample batch pixels and model, and then the rest is gonna be, and then image shape. It's gonna be config.num channels, config.image size, config.image size. Our image size we're going to make really small for, right, because we're just trying to confirm we're not going to do high resolution large images for these examples that I'm doing, right, for these experiments, because I don't have the money to pay for that kind of training, right, and we want things to go fast. So for now, right, if I had the money, then I would spin up 4 or 8 A100s or H100s and I train these models and get really cool results, but I can't spend $100 an hour, you know, not right now. So soon, once I start working again. So, all right, sample batch pixels is going to return samples, and then we're going to pass samples to log samples, right? Log samples. Number of rows, we're going to leave that as 4. Step is going to be, that's for weights and biases. That's the group, that's the identifier it's going to use for the entry that it makes in its database. It's going to be epic. What else is there? Yeah. Prefix is going to be samples. Okay, cool. And then we're going to do log dict step epic commit true. I'm going to log things at the very end of the loop. Yep, this looks good. Okay, so this is our training loop. Okay, and then here we need to do loss is going to be equal to v red minus v star. So it's loss is going to be this, right? Squared L2 norm. So root by 2 and then mean. So we're going to do the average L2 norm, squared L2 norm for the batch, and then loss, and then optimizer dot zero grad loss dot backward optimizer dot step, right? And then we have now we have train epoch loss is going to be plus equals 0. So now we're going to add, right? Boom. And then once we come out of the loop, we can divide equals by, right, to get the average loss for that batch. And now we can write that loss here, okay? Then we can do and then we can say boom. We're going to replace all those, okay? This looks good. How much time? It's 18 minutes already. Sheesh. Okay. So let's see if I can finish this up in 10 minutes. All right. So now we have to do compute data. Okay. So compute data, we're going to say images. Let's say we're going to give, so this is what we need to do. We need to compute this equation. We need to, and to do that, we need an x0, which is our images. We have that. And then we need x1, which is our, so we need a sample from a standard normal, and we need t. So we need a sample from standard normal, and then we just need to sample t between 0 and 1 uniformly, okay? So we need our Gaussian. So first I'll say x0. X0 is a flattened image vector. So let's use this, use the same language. So images dot to device, okay? X1, right? So we're sampling, we need to sample our data here. This is our expectation. This is a subscript of our expectation. We see xt here, but to get xt, we need x1. We need a sample from a standard normal. So torch.rand n for standard normal, and then like, I have, I'm just going to do like x0 device equals device for when we move this to the run pod VM. Okay, so now this is going to be BCHW, right? This is also boom. Okay. Now T is going to be torch.rand from a standard normal, and then BCHW. Actually, I can just rand x0 dot size, boom, b device, okay, this is going to be b, right? Now, so I have all the samples I need to compute this 1 minus t x naught t x1 plus t x1, right? So xt equals 1 minus t times x naught plus t times x1. Now we want this to be shape this. It's going to be in the shape of a, so it's going to give us exactly where the position along this straight line right here between x1 and x naught, right? It's going to give us our xt. We're parameterizing that straight line. But to do this, we need to broadcast t. Right now, t is of shape b, we need to make t of shape b 1, 1, 1 to do element-wise multiplication, right? So to do that, we're going to say t is going to be b 1, 1, 1, right? That's going to be our t. Okay. Boom. Now we have that, and now we just need to pass it xt and t to our model. So we're going to say model xt t, and this is going to return our prediction, our predicted velocity. And then v star is x1 minus x naught equals x1 minus x naught. Return v star v red. Boom. Exactly what it's expecting up here. Now our model, which is UNet pixel space, its forward is expecting an xt and an xt and a t, right? Xt dot shape is going to be b c h w. T dot shape is going to be b. That's what it's expecting. Now for this example, I'm just going to make a simple MLP dot sequent or dot linear, where the dimensions I think the image size I'm using is oh shoot. Image size is 32. I'm just gonna send the width dimension through a linear layer just so we have some gradients. So 32, 32 xt. Okay. And comment this out. And let's run this. Let's see what happens. Do you mean num channels? Yes, I did. And epics. Yes, it did mean and epics. See if it trains. Let's see if the module has the yeah okay, good. So it recognized. I didn't add linear as a class variable, but the module still picked it up. It still picked it up under the forward method. I was wondering if I had to name it up here in order for it to register the parameters, but we're good. See the loss, that's expected. We're expecting it to be pretty high. So I want to do something. I want to get I want to print the magnitude of the pred So I want to do something. I want to print just for debugging. So if dconfig.d v star dot, I want to get the magnitude I want to get the average magnitude of the velocity, which is our ground truth, and the prediction. And I want to print v hat v star. So magnitude v star is going to be vs mag 0.3f. And let's do them in the same. Magnitude v hat v 0.3f. Yeah, let's do this. Let's make a little helper function. V star print mag wait. Oh, I had duplicates up there. Okay. Get or print mag v star v pred. Okay. Yeah. We can just put it on the same line. Oh, I haven't computed the loss. Boom. Okay, let's run this. I like that. These loops are nice and tight. Now we should see the prediction slowly get closer and closer to the magnitude of the prediction slowly get closer to the magnitude of the ground truth of the derivative of the trajectory. What does it say? Okay, wait a minute. So this is a torch dot tensor. So v star dot oh. Absolute value. It's not running. It does this thing where it hangs sometimes. It's strange. Okay, there you go. Time are we at? Already passed. All right, so let's see what happens. It's probably going to be a bit noisy because we don't have large samples. So batch size is 8. Sample size is 32. Let's make it larger. 128. Batch size 4. I want it to loop through these. I want it to be more like stochastic gradient descent. Yeah, I mean, I don't expect these to increase actually. Yeah, I don't know why I'm even thinking that. I'm using literally an MLP on the width channel. That doesn't even make any sense. Like, I don't even want to think about what that's actually doing. But okay, our training loop, this is good. This looks good. We'll get to verify it in the next video. Oh, let me do inference. Well, I'm at 35 minutes, so let's keep these short. I promised I would make these shorter. And so I'm going to end this one here. The next one, I'm going to code the backbone, UNet, and then we'll see how that'll probably take me about 20, 30 minutes, and then I'll do inference in another video. I'll try to keep these modules shorter, and you can just watch them back to back.